Hello dear students, today we will discuss the filtering based problems using discrete Fourier transform. So like we have covered some of the filter design problems using Z transform. So in this we will see how we can use discrete Fourier transform in the implementation of filters, mainly the digital filters. So we'll see one problem in this. So it is that you have to determine the response of a digital filter, and we are given with impulse response Hn, that is given as 2 2, means you are given two coefficients with n0 and n equal to 1, and we are given with the input sequence, that is xn, and it is given as again two values are given 1 2. So n equal to 0 means it is 1, and at n equal to 1 it is 2. So now what we have to find is we are given with Hn, that is impulse response, we are given with input, that is Xn, and then we have to find the response of a filter, means I have to find Yn. Now again, one method we can apply, we can go for convolution, but because if I want to calculate the response, for that I need to calculate linear convolution. So here we will see how we can implement that more easily in frequency domain by converting the signal to frequency domain, and then we are calculating the Yn. So now if we see that the length of xn is 2, it is given, let's consider it as capital L, which is equal to 2 because it is present at n equal to 0 and at n equal to 1. Also if you see Hn, so length of Hn is also 2 because again it is present at n equal to 0 and n equal to 1. So let's consider that length as capital M, which is also 2. Now we know that if I want to calculate the convolution, or if I should determine the length of the output sequence, that will be length of first sequence plus length of second sequence minus 1. So we are given with this capital N, which is capital L plus M minus 1. That means we are calculating the length of the output sequence. So L here is 2, M here is 2 and minus 1, so you are getting 3. That means now I have to calculate 3-point DFT. I have to calculate 3-point DFT, but it is always better to use standard DFT values. So what we are doing is we are using standard 4-point DFT to calculate this. That means we are considering this capital N as 4. Now if we are considering this capital N as 4, that means I have to increase the length of Xn as well as Hn should be equal to 4 if I want to apply DFT. Because when we solve this, actually it will produce convolution, circular convolution. So, but our motive is to get linear convolution. So how we can convert that circular convolution into linear convolution? For that we have to change the length of the sequence to L plus M minus 1. That means length of first sequence plus length of second sequence minus 1. So we have to calculate according to that. So for that what we are doing, we are making the length of both the sequence, you can see Xn and Hn equal to 4. How we can do that? We can do by padding the 0. So we are padding zeros at the end. Mainly we need two zeros because previously it was of length 2. Now we want it to of length 4. So what we are doing? We are keeping these two additional zeros. We are padding these two additional zeros at the end So now the sequence will become of length 4. So xn will be 1, 2, 0, 0, and similarly hn will be 2, 2, 0, 0. Now how we can convert that convolution into frequency? If we have convolution in time domain, that will be multiplication in the frequency domain. That means to have convolution of xn and hn, I can have first xk, that is DFT of xn, then I can have hk, that will be DFT of hn. Then I will multiply both the DFTs to get yk, and finally I will get yn by taking inverse discrete Fourier transform. So our next step is we have to calculate xk. Now how we can calculate xk? So we have DFT formula to calculate xk using this Twiddle matrix W. This is capital W represents the Twiddle matrix. So here capital N is 4. That means I need fourth Twiddle matrix. So Twiddle matrix can be given by, it is actually e raised to power minus j, you can see this, 2 pi by 4 n k. So we will keep, and n will run from 0 to 3. Similarly k will run from 0 to 3. So we can keep these values and we can solve this exponential, complex exponential, and we'll get W4 matrix. So this will be W4 matrix. We can solve this by solving this complex exponential for various values of small n and small k. And then, so this is xn and wn, and xn we can obtain whatever given to us, we can keep like in column. So 1, 2, 0, 0. Now to obtain xk, now we are obtaining xk. So this is how we are getting xk. So xk matrix is this W matrix into x small xn matrix. So you will multiply these two and we will get the values corresponding to capital Xk. That means again we know k will run from 0 to 3. So you will have 4 values. That is x0, which is coming out to be 3. We have capital X1, which is coming out to be 1 minus 2 iota or 2j. Then capital X2 is coming out to be minus 1. Capital X3 is coming out to be 1 plus 2j. So you should remember, they will, if there is any conjugate value, it will come in complex conjugate pairs. So you can check that whether your DFT is correct or not. So now we got the values of capital Xk, that means DFT of Xn. Now what is the next step? Next is we have to similarly calculate the value of Hk. So again we will apply this matrix method to calculate the value of Hk, and it is given like this. Directly I have written these values, but we can apply the same method. We can use W4 matrix with Hn to calculate this Hk. So you will get this Hk, it is coming as 4, 2 minus 2j, 0, 2 plus 2j. So this is Hk. Now what is next step? Next step is we have to obtain Yk, and Yk is multiplication of the two DFTs, that is Xk and Hk. So you will multiply these values, point to point multiplication we have to do, and you will get these values. You can see, so we will obtain Yk as 12 minus 2 minus 6j, 0 minus 2 plus 6j. Again you can see if we are having any conjugate value, that is coming in complex conjugate pairs. So this is Yk. But what is our motive? What we need to find? We need to find Yn. So our next step is to obtain Yn. And how we can obtain Yn? So Yn can be obtained by the inverse discrete Fourier transform of Yk. So now we will see how we can calculate the inverse discrete Fourier transform of a signal. So here it is Yk, capital Yk, and we need to find the inverse of this, that is Yn. So the formula again we can use the Twiddle matrix, but the conjugate of twiddle matrix. And what is the one more change? You will have this 1 by n factor in inverse formula. Now, how we can get the conjugate of this W matrix? So it will be complex conjugate, means we can derive by just changing the sign of plus j term to minus j, or we can say minus j to plus j, to obtain the complex conjugate of Wn. So we know W4 matrix. Here also we will use W4 matrix because Yk is again of length 4. So you will use W4 matrix, but now we will use the complex conjugate of W4, and that can be obtained by just changing the sign. You can see we can obtain by just changing the sign. So you have changed the signs. We have minus j has become now plus j has become minus j, again this plus j has become minus j, and minus j has become plus j. Other values will be same. So now we will apply the formula of this inverse DFT. So yn will be, again it will have 4 values: y0, y1, y2, y3. This is 1 by n. Capital N is 4, so you will keep 4. This is W4 conjugate matrix, and these are the values of Yk. So again we will do matrix multiplication, and finally we will divide the values by 4, you can see, and we will get the values corresponding to Yn. So this is 2, means it is y0, 6 corresponds to small I 1, small y 1, and then 4 is for y2, 0 is for y3. So you can see, because the length of yn should be 3, so automatically this 0 will appear at 4th location, and actually yn is of length 3. So we have got 4 length because we have used a signal additional 0, because we need to calculate 3-point DFT, but what we have done, we have calculated 4-point DFT. So this last value will come automatically as 0. So ultimately what will be yn finally? Yn will be of length 3, that is L length of xn plus length of hn minus 1, that was 2 plus 2 minus 1. So that was 3. So yn is coming out to be 264. So this is the required response of the filter. So this is how we can determine the response of the filter using discrete Fourier transform. So let's revise the steps once. What we have done, we were given with xn and hn, and we need to find yn. So what we have done is we have implemented it in frequency domain. So first we have calculated the DFT of xn, that is capital Xk. Then we have calculated DFT of hn, that was h of k. Then we have multiplied the two DFTs, that is xk into hk, to obtain yk. Then last we have converted that yk into yn using inverse discrete Fourier transform, and we have implemented DFT and IDFT using matrix method using twiddle matrix. So this was all in this lecture. Thank you so much.